Kinetic molecular theory is a model that describes gas behavior. Unlike the ideal gas model, which is derived just from empirical measurement, that is, we go in the lab, we change the pressure, we change the temperature, we change the volume, and we see what happens, and we come up with a mathematical formula that essentially replicates the physical data. Kinetic molecular theory is a physical model. That is, it starts out with some basic physical assumptions, and then it says, if I just crank through the laws of physics, what is the end behavior that I predict? And kinetic molecular theory has four basic assumptions that it starts with. The first is that gases are discrete particles, and those particles are very small. So that is, of the total volume, the particles occupy very little space. The second is that those particles are always moving. And so they're not fixed in space, but they're always traveling around and occupying different parts of the volume. The third is that the particles don't interact with each other at all. That is, they have no repulsions for one another, and they have no attractions for one another. And so they're essentially only interacting with the sides of the container. And the last one, and probably the most important part about kinetic molecular theory, is that the kinetic energy of the particles is proportional to the temperature. So if you start with those four basic principles, and then you say, I want to calculate the pressure, you now have a volume, you have particles moving around, you know how fast they're moving around, and so you know how many times they hit the wall of the container. You know their mass, you know their velocity, so you know how hard they're hitting the walls of the container, and you can calculate the pressure. If you do it, and you run through all the math and all the geometries, lo and behold, the behavior that you predict at the end of the day is identical to that from the ideal gas law. That is, you end up with the behavior that we see in the real world for gases, at least in conditions of low pressures. The most important thing to take away is that the kinetic energy is proportional to the temperature, but not all particles are moving at the same speed. So when we think about how to model the motions of the particles, the average kinetic energy is proportional to the temperature, but there's a distribution of kinetic energies. So some particles are moving really fast, and some of them are moving very slowly, but on average, we know how fast they're moving. And that's important not just for understanding gases, but it turns out it's going to be important for understanding phase changes, melting, evaporation, and it's really important for understanding the rates at which chemical reactions take place.